to section 7.2 and 7.3 tonight. We will see when I get done with 7.2 what your faces look like. And I'll decide if I'm going to do 7.3 or not. I have time built in, like, because I don't necessarily have to do 7.7 and 7.8, so it won't change the actual schedule or anything else like that. That's why I design it this way. Normally, I don't end up going in through do 7.3. I normally just end up doing it in 2 separate nights, but we'll see. All right, so we're going to start looking at trigonometric integrals. So let's start off with the simple one. Cosine 3x, or the cosine x to the third power. How would you like to do this one? And if you know, don't say a word. Because I know you've seen some of this stuff before. What would you like to try? Okay, do we have a trig identity for cosine to the third? I know I have one for cosine squared. Okay. So first thing, actually, just so everybody's clear, because actually, believe it or not, actually I found out that not everybody knows this. This is the same thing as that. Those mean the exact same thing. It's just a different way to write it. Yeah, now that I'm going through and writing things and writing books and stuff, some people are like, wait, that means yes, that means the same thing. So, all right, so let's break it up. No problem. So let's change this to cosine squared x times cosine x. Okay. Now what do we want to do? Yep, so we can use the Pythagorean identity. So we have, remember, sine squared x plus cosine squared x equals 1. And we can manipulate that any way we want. So we're going to change that so this is 1 minus sine squared x cosine x dx. Okay. I don't know about you, but this problem doesn't seem to be getting simpler. No, I'm not necessarily saying nothing we've done is wrong. All right, everything we've done works. So there's a thing about like mathematically doing something wrong, which we haven't done yet, and then just not necessarily making the problem easier to do something with. So the question is what are we doing? Is this making the problem simpler or more complicated? We're just doing things to change things. Like where should we go with this? So we kind of changed it to a multiplication. So we have a product. We have 2 things now. So we could do integration by parts that we had. So basically, the only 2 things that you know now is either you know the rule, which in this case, obviously we didn't, or we have u substitution and integration by parts. I wouldn't have taught this if you weren't going to use at least something that I've already taught you. So do we want to try to do integration by parts, or do we want to try to use substitution for this one? All right, so let's try u substitution. So now the question is what do I want to make u? So if we go back and look at this step, or even the step at the beginning, like even if we go back here, all I have is cosine, right? So if I take u and make it cosine, what's du going to be? Yeah. Bad computer, touched the wrong button. So I have negative sine x dx. Okay, so I got that. Problem is I don't have a sign in the problem, right? So that doesn't really help me. So That's typically what most people would have tried to do first. It's like, okay, let's try some kind of U substitution. And if you broke it up, we got it broken up here. We now have two cosines, which, okay, now I can change it to sine. But the problem is this sine's sine squared and it's inside parentheses. So instead of doing it that way, so we know cosine goes to sine. What does sine go to? Sine goes to cosine. So let's make u sine x. So du is cosine x dx. Hey, look, I have a cosine x dx. So believe it or not, everything you tried actually was exactly what you had to do. But when you're looking at it, it just wasn't getting simpler. Like the problem, you were making the problem more complex, but you needed to in the situation. All right. So we have what u is sine. We have the cosine x dx, so that's great. So now I can basically rewrite this problem in terms of u. So I have the integral of 1 minus u squared du. Now, that problem's pretty simple to do the integration of. So that's going to be u minus u to the third over 3, right? Because 1 becomes u. And then the u to the squared becomes u to the third divided by the 3. So now, remember, you always have to go back to what we had. So we want to go back to my u's. So my integral of cosine to the third x dx equals sine x minus sine to the third x over 3 plus c. And that's it.
Just on the way, but can we take its derivative just to make sure it comes to like plus the third x?
Yeah, we can do the derivative of this one. Yeah, we can do that. To verify, not a problem. Always a nice thing to do is to check your work. So let's try it. So we've got, let's do this part. Oh, actually, I'm going to just put that in there because we have to do this as two separate things. So we'll do this. What's the derivative of sine x? Okay, so that's cosine x. Okay. Now this one, I have to do the chain rule on. So we've got negative sine to the third x over 3. So we're going to do the derivative of sine x, which is cosine x. And that's going to be times then we're going to bring down the 3. So I get negative 3 over 3 sine to the squared x. Sine squared x. Right? Okay. So I have cosine x. A little bit. So cosine x plus cosine x times negative sine squared x. So I can pull out a cosine x, and I'm left with 1 minus sine squared x. So then I have cosine x times cosine squared x, which is cosine to the third x. So it works. And if you notice, your derivative steps, very similar to what you did over here. To break it down. This was the last step in the derivative, then we went to that, then we went to that. So there is some connections between the two of them. Okay. All right. Let's look at this one. So now this one's got both of them in it. So the last one just had the cosine in it, and I somehow needed to get the other piece. So now this one's got sine to the fifth x and cosine squared x. So which one do I want to make u? Because if we think back to what I just did in the last one, the goal is to get the derivative of it, right, to be left over. And everything else has to be in terms of the other one, in terms of what u is. So do I want to make u sine or do I want to make u cosine? Okay. If I make u sine, my du is cosine, right? So I would have u to the fifth. Now this cosine I'm going to have to split, right? Because I only want one of them. So I'm still going to have a cosine x du. So that piece right there is kind of screwing me up. Because that becomes that. And that goes down. So u being sine doesn't really help us here. So let's try the other one. So if I make u cosine of x, du is negative sine of x dx, right? So that's negative du is sine of x dx. So I need one sine pulled out. All right, so let's see. So if I do that, I have sine to the fourth x, cosine squared x, sine x dx. Okay, so I now have that is there. So that's going to be that. And my u is cosine, so I can get rid of that. But somehow I need the sine 4x to become cosines. So what's the rule that allows me to change sines and cosines? Yeah, the Pythagorean identity, right? The one we just used a minute ago, just the other direction. So sine squared x equals 1 minus cosine x. Now, if I have it to the fourth, that's going to be squared, right? Because if I square that, that's to the fourth, and that's no. Correct? Okay. So I have 1 minus u squared squared times u squared du. All right. So now I just got to do the integral of that, right? My suggestion for this, let's multiply it all out. Let's not try to do the u substitution with the 1 minus u squared and all that. Let's just multiply it out, get it clean to make it simpler to do. Because otherwise, we're going to have to do the product rule and a bunch of other stuff, and it's just a mess. So this becomes 1 minus 2u squared plus u to the fourth times u squared. So I have my integral of u squared minus 2u to the fourth plus u to the sixth. So now we can do the integration of this. U to the third over 3 minus 2u to the fifth over 5 plus u to the seventh over 7 plus c. That's way, way easier than going through and doing the product, the integration by parts and everything else for that top piece, which kind of would have been messy. So whenever you have, so one of the things, if you're trying to do integration by parts, you kind of want two different things. If it's all algebraic, try to simplify it down first. You might be able to actually eliminate the process of doing it. Same thing like here, if they're both trig functions, like there might be some other way to look at it than trying to do integration by parts. All right, we have to do one extra step. You have to change it back. So in this case, my u was cosine. So this becomes 1/3 cosine to the 3x minus 2/5 cosine to the 5x plus 1/7 cosine to the 7th plus c. All right, let's see. Yeah, I want to do a work for that one. Everybody good with this one? Because you're up next. All right, try this one. See what people are trying. U's either going to be sine or cosine. Because if you make you that, then you're going to have to do the chain rule on that. Because it's not that it's more complicated, but then you have to figure out if you have the stuff over here, break it out, and you might not. Okay, so you made your new sine. It's fine. So your goal is to make everything except for one cosine sine. That one. Just there. Okay. Now your goal is to make all the cosines over here. You need one for this. So all the rest of the cosines have to be sines. So that's your piece there. So that. All right, you only ever want to do this. You don't want to ever try. Because your goal is to get them all to be one thing. So we need new sine, we use cosine. Okay. So then we want them all to be, we want all these to be sines. So we do that. That's fine. So if we change that to that, we don't get cosine. You're missing a cosine. Hello. Hey. Calc 2? Reminder.
So the audit is fast.
Oh, okay. That's not a problem. You're more than welcome to. All right. So pretty much every one of you did the same thing. Which is, let's see if it works. So you made you sine. I think everybody did that. Oh, I didn't actually look at you. So okay, I take it back. Everybody but him. So made you sine. And then we had du is cosine, which is fine. So now the goal is I need to have a cosine left over. Okay. The next thing I saw pretty much everybody do was they said, okay, so I've got cosine squared. To make this nicer, cosine squared x equals 1 minus sine squared x. And then we did that to the third power, did that to the third power. So, okay, now I got rid of my cosines. So we have 1 minus sine squared x to the third, sine to the third y, dy. Great, everything's in terms of sines. I don't have a cosine. I'm missing the cosine to be able to do that. So somehow I have to pull that cosine out. But if I pull the cosine out, now that's only cosine to the fifth. And I can no longer do that. Okay?
So it's like when you're pulling something out, you want to be working with even numbers?
Yes, that's the key. You want even, because if I have an even thing, I can do this. But if I don't have an even power, I can't do this. So the one you want to pull out is the one that's odd. Because this way, then you only have even things. And even things are nice. So, That was what I was kind of hoping people would catch. And it was very good you caught that. All right, so we're going to make u sine. So that means du is cosine of y. Oh, sorry. I switched it around again. I went the opposite way. U is cosine. And that's going to be negative sine of y. Good. So I'm going to have cosine 6y, sine squared y, sine y, dy. So now this piece right here is equal to that part right there. And then we can change my sine squared y into 1 minus cosine squared y. So I now have u to the 6th, 1 minus u squared du, and the minus sign. I'm trying to clean up this in front so I can write it in front. Because we still had that minus from the sine y. And in essence, anything that's here, you can just pull out in front of your integral. All right, so now let's clean this up and do the integration. So I have u to the 6th minus u to the 8th. So I have u to the 7th over 7 minus u to the 9th over 9 plus c. So I have cosine to the 7th y over 7 minus cosine to the 9th y over 9 plus c. Yeah.
Why is it u to the 8?
U to the 6 times u squared. Distribute the u to the 6th. Yes. Oh, you're right. I did forget the negative sign. Good catch. So technically my sign switch. Good catch. Huh? Did you miss yours too?
No, my answer is if that I found the negative sign because I took it over as negative du.
Oh, okay. That's fine.
I just put it. I put it on the outside.
Yeah.
I don't know. It's just the way I lined it up. I did
Yeah.
vertically. So
Yeah.
using, like the arrows. It was like right there. Like it's good.
Yeah, I run out of space doing things vertically. I'm limited by the rectangle on my screen. So it's like I can rotate it, except then it rotates up there too. And it would make it smaller and would be nice for you to look at. All right. Yes. Yes. I don't have that in the Jamboard. I don't really feel like switching over to OneNote because then I can't just stream the tab. Any questions with this? So what are we looking at? For my du, I always want that to be the one with the odd number. So in this case, I wanted my du to be sine because that's what I get to pull out. So that my u's got to be the opposite. So the u has got to be basically what my even thing is, which gives me that piece that I'm going to pull out. So here's the rules. I'll talk about that one in a minute. So actually, this one over here. All right. So, in essence, this is basically exactly what we just talked about. So, if the power of cosine is odd, then I'm going to use the cosine squared x equals 1 minus sine squared x. and I'm pulling out that one cosine x. So I'm changing everything into sines, and I'm pulling out that one cosine x for my du. And my substitution is u equals sine of x. If the power of sine is odd, then I'm going to do the opposite. I'm going to use sine squared x equals 1 minus cosine squared x. I'm going to substitute u equals cosine x, and I'm going to have that sine x dx for my du. So then we have to do something else.
Fair enough.
So we'll get there. I have one more thing I have to do with this one anyway. Notice though, however, it doesn't say you have to have the other one. Because actually in the very first problem that we did, we only had an odd, was it cosine, right? Yeah, it was cosine to the third x. So you don't necessarily have to have a sine because we can basically make it by pulling the one out anyway. All right, so the question comes, well, what happens if they're even? So if they're odd, you can use either one, by the way. If they're both odd, you can use either one of them. They'll both work out to be the same. The big one comes though is if they're both even, because if they're both even, when I pull one out, I'm left with an odd and I can't change it. So if they're both even, we have to use a half angle identity. So sine squared x equals 1/2 1 minus cosine 2x. And cosine squared x equals 1/2 1 plus cosine 2x. Notice, they're both exactly the same except for the symbol and the sign and the sign in the middle. So the sine squared is 1 minus, the cosine squared is plus. But it's always 1/2 1 cosine squared 2x. So that's always there. And sometimes we can use this wonderful little identity, the sine x cosine x equals 1/2 sine squared, or sine 2x, not squared x. If we're left with just sine x and cosine x, that allows me to change it to a sine. All right, so now that we've got that, let's actually do this problem. All right, so I got sine squared x. So let's change it. So that sine squared x is going to become 1/2 1 minus cosine 2x dx. The 1/2 can go out in front. So then I have 1 minus cosine 2x dx. So what is the integral of 1? That's x. What's the integral of cosine 2x? Keep going. Almost positive sign. Because it's going up. Remember, because that's there, I have to do that U substitution. But remember the trick I told you on Tuesday? If there's just a single number there, you just pull it out and make it a fraction. So that's going to be 1/2 and then sine 2x. 0 to pi. All right, what else is different about this problem? It's a definite integral, so I have to plug in my values and solve it. So I have 1/2 pi, sine of 2 pi is 0, so it's actually just 1/2 of pi. And then plugging in 0 gets rid of everything, so the answer is pi over 2. So that those rules, the half angle and the other identity, is very helpful when we're doing these things. There. All right, try this one. If you don't like t's, you can change them to x's. I will end up changing them to x's as soon as I write it. My t's look like pluses. Okay, so that's close. That's fine. That's fine. You have one sign left over. We still have to, you have to use the equal. So somehow you have to use what I just showed you.
changing that. Done. Okay. And you change that to that. Okay. And then we should do that. Okay.
Let's see where we're going with it. Trying something. Okay, so that you distributed it. It's fine. The problem is now have to do your substitution. And we don't have to solve. Remember, if they're both even, you kind of have to use the rule we just talked about. Your handwriting is so nice. All right, so you're changing everything over that. You're missing actually with the full square? No, put that to the fourth. To the fourth? Yeah. That's okay. That's going to change your work. What you actually did there was totally right, by the way. But that was going to make it a little tough. Okay. So you're just auditing. That's totally fine. I'll just leave it nice a little bit. I post everything online too. So if you want to go back and look at the stuff that you're planning to do, classes do this, you're going to. Okay. So basically everything the same. I don't give up homework and stuff like that too. It's just the tests which you want to take. So, right. Yeah, so, but yeah, if you have any questions or anything else, I'll give you the syllabus, you're more than welcome to ask questions. Everything else is yours. Okay? Oh, you're missing the square. Yeah. Yeah, you didn't, I didn't keep it over there. Okay, so again, remember, they're both even. If they're both even, I'm going to do leftovers or not. I can't do that. Remember, when we do that step, I need to have the evens left over. When we have they're both evens. All right. Go further down the rabbit hole. All right. So a lot of you started working on doing it the way we did these, which is fine, except remember, I need to have evens left over. So if I take one away from an even number, I have an odd left over, and I'm kind of it stuck. So that's where this rule comes into play. So this rule allows me to take it and break it down to a point where I don't necessarily have the other piece there. Get rid of the exponent, basically. So just this. All right, so I've got this. So if I change my sign squared, that's going to be 1/2 1 minus cosine 2x. So that's that sine squared part. And now if I do my cosine, I have cosine to the fourth. So that's the same thing as saying cosine, this right here is cosine squared x squared, right? So I can do this, I just got to square it. So it's 1/2 1 plus cosine 2x squared. All right, so I have a half here and a fourth here, basically. So I can pull out an 8. So I'm going to take out that number there, so I don't have to worry about that. And now I'm left with 1 minus cosine 2x, 1 plus cosine 2x squared.
That's actually where I was headed with it.
Good. All right, so now the only part that's going to cause me any problems is I have to deal with that squared. So let's take this, multiply it all out, and see what I got. So this part right here becomes 1 plus 2 cosine 2x plus cosine squared 2x. All right, so we're now to that point. So now we can change that, right? By doing that. So this is now 1 plus 2 cosine 2x plus 1/2 1 plus cosine 4x. Okay. We to there? So
The 1/8 is.
the 1/8 came from, and I'm going to do this in a different color that you're probably not going to be able to see, but that and that. That's the 1/8.
Okay.
Like I figured you might be able to see some kind of color up there, some kind of line.
No, I was thinking also it came from the power of 2 as well.
Yeah, that was the 1/2 squared, which is the 1/4. That's
Yeah.
That's where that 1/8 came from. So we just pulled that out so I don't have to deal with that, because otherwise it'd have been a mess going through the rest of the part. All right, so let's clean this up. Let's see. So that's 1/2. So I have 3/2 plus 2 cosine 2x plus 1/2 cosine 4x. This is messy. And I have this whole thing. We still have 1 minus cosine 2x in front of this whole thing. Okay. So we're here. I'm running out of space. I need another slide. All right. So I now still have to multiply this, right? Okay, let's see what we got. I don't think this is coming out nice. So we might have to try a different way. So we got 1 times that, so 3/2 plus 2 cosine 2x plus 1/2 cosine 4x minus 3/2 cosine 2x minus 2 cosine squared 2x minus 1/2 cosine 2x cosine 4x. Because I can't put those together. Literally all except for that piece right there. We can do all the rest of the stuff. Those integrals are easy. That's not. All right, so up to this point, have I made a mistake? No. Everything we've done is correct. Everything we've done there is correct. I was checking it before I wrote that all down. But run into a problem. And this is gonna happen. So the question is that since everything I did is right, I either have to try a different method or I have to figure out how to integrate that. Because even that I can change back to the 1 plus the 1/2, because that's that simple. But that I have to figure out how to integrate, and we don't have anything to integrate. We can do integration by parts, but I don't think it's going to come out nicely working down because cosine is going to switch to sine. Actually, let's try it. Integration by parts on that one might actually work. Okay. So, well, in this, there's actually a reason behind what I'm doing, because a lot of times I have the actual book answer the way they did. The book did it totally different. The problem is that when I'm going around looking at things, people are trying this. So with trigonometry especially, there's multiple ways that you can go about solving the problem and get the right answer. Your answer might not look the same as the book, but that doesn't mean it's wrong as long as you did all your steps correct. So what we've done is totally correct so far. It's messy as all heck, but everything's correct. Okay? So we've just got to figure out if we can actually do the integration for it. So we can change this part right here. We'll change that part in a minute, but I want to. So let's actually go through and we'll do the integral for each part. So we have the integration done, and then we'll come to that part there. So the integral of 3/2 is 3/2x. The integral of cosine 2x is 1/2 sine of 2x, right? Yeah. So that's just sine of 2x. Cosine 4x is going to be 2, no, not 2, is 1/8 cosine, oh no, sine 4x. Sine 4x. Oh, I totally forgot. I almost forgot the 1/8 in the front of this whole thing. All right. Then we have minus 3/4 sine 2x. So we've done that one, we've done that one, we've done that one, we've done that one. Those two I could have actually put together. All right, let's do that part. So cosine squared becomes what? Was it 1/2? So that's 1/2 1 plus cosine 2x. And then I had a -2 in front of it. So that's just -1. So then I have Okay. Have I lost you yet? Huh? Did I lose you before I did the integral? Okay, that's fine. I'm not going back that far. Not going back that far at this point. And so we're done here. So basically, I want to be able to do the integral of all of them. So we got the integral of that. The integral of that. So remember, if there's a number inside, we just flip it over. So that's 1/2 times 2 is 1. That's where that 2 went. This one ends up being 1/4 times 1/2, which is the 1/8. Sine 4. This one, 1/2 times 3/4 is 3/4. Sine 2x. And now I took this piece and I changed it, did the exact same rule I did at the beginning. I took the cosine squared and changed it into, x, it should be 4x, not 2x. Because I have a 2x inside of it. All right, so now I got to do the integral of that, basically. So that's going to be negative x and negative 1/4 sine x, or sine 4x. All right, now we got that cosine 2x and cosine 4x, and let's see if we can do something with that, which I'm not totally sure we can. So we're gonna try. But the good news or the bad news? Bad news is we might have to actually redo this problem with the other method. It's possible. The good news is I'm not doing 7-3. All right. Let's try to do the integral of this. So we're going to have to do the partial fractions. So we've got u equals du, v, dv. So actually, it doesn't make a difference which one we set to which. So let's just make that cosine 2x and that cosine 4x. So this will be 1/2. That'll be negative 1/2 sine 2x. And this will be actually that's not negative 1/2 because that's the derivative. I'm stuck in the integrals. So that's just 2 sine 2x. This one's 1/4. And it's sine 4x. Yeah, I'm still going to end up having this. We're still going to have. So the problem that we have is there's no real easy way to deal with two different angles like that inside of a function. So, and even when I'm doing this, my second integral piece that I'm going to have is, remember, it's u or it's v du. So it's 1/4 sine 4x times 2 sine 2x dx. So I'm still stuck with the 2x and the 4x. So this method doesn't, well, it does work. We got it mostly down there, but I can't finish the integration with what we know currently. All right. So we have to try something else. After 3 full slides of work, we have to try something else. Well, yeah, I changed the t to an x just because I hate writing t's. But that wasn't the problem. All right. There was 2 things on this slide. The second one is sine x and cosine x equals 1/2 sine 2x. That's also an option. So let's try that one. So we have sine 2x, cosine 2x, cosine 2x dx. So the rule stated that it was sine x cosine x equals sine 2x. Right. I always have to look these up because I never remember those little ones. 1/2 sine 2x. So it was sine x cosine x equals 1/2 sine 2x. All right. So, but I've got it squared. So I've got to change this to sine x cosine x squared, which then gives me 1/4 sine 2x squared. One half, not 1/4. I was one step ahead. Cosine 2x dx. So this now is 1/2 sine squared 2x, or 1/4. And cosine squared x dx. Huh? No, this actually is simpler at this point. All right, so now we can multiply. Oh, I forgot to change my cosine. Another slide, running out of room again.
Changing cosine squared x.
Yeah, 1 plus that one. Yeah. All right, so I got 1/4 sine squared 2x times 1/2 1 plus cosine 2x dx. So I'll pull out the 1/8, so I don't have to worry about that. And then I have sine squared 2x plus sine squared 2x cosine 2x dx. All right. So we can now split this into each piece, the integrals of each piece. So let's look at this part first. So we just did that one. Sine squared 2x, we did that one. That's right there. And that's the answer. Huh? No, we're just going to rewrite it. But that sine squared x is this. The only difference is we didn't use x, right? We had 2x. So it's going to be 2x and 4x. So I've got, so this part is 2x plus, what was it, sine 4x? If I remember right. 1/2 sine 4x. So that's that part. And now let's do the integral of this. Now, this one we can do integration by parts on because they're both 2x. All right, so we've got the integral of sine squared 2x cosine 2x. So we'll make u where
The left side,
this one?
yeah. There should be a
Wonder if this should be 1/4 because it was 2x because we did the 2x.
No, like on the outside. So you could go back to the previous one. We did a definite integral with it, but there's like a half outside the left. I think you dropped that.
Oh, you're right, it did. You're right, it did. Now you know why trig sucks. It's okay. I only have 20 slides and I'm at 20 now, so I can't do much more extra work. You're going to be saved by the wonderful thing of Jamboard. All right. So we've got u equals cosine 2x. Du equals 2 sine, oh no, yeah, negative 2 sine 2x dx. dv equals sine squared 2x, which we just did. This is why math teachers always do their work ahead of time and put it out so we don't have to do it in class, which I never do. Because then we pick problems that work out nice instead of problems like this that don't work out nice. Yeah. And we're still back to that problem. What the heck?
I was gonna say, if this is stumping you, then I'm like,
No, it's not. It's just a matter of it's just
Can we do substitution for this and pull out a
Can
you with sine 2x? And
oh yeah, you could. That solves the problem. That solves the problem. Ay, 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 ay. No. So yeah, we'll make that sine 2x. So du is 2 cosine 2x dx. So it's 1/2. There we go. That's what's the problem. So this becomes u squared with the 1/2 in front. So I get u to the third over 3. So it's times the 1/2. This part right here. I got to bring it over.
Oh, yeah.
Hey, I got that half. Okay, so my final answer. As everybody's happy. And I'm not doing the definite part of this one because actually I think it was a definite over at the beginning, and I'm not doing that part now. Huh? Yeah, I'm not plugging numbers. Bring me. Plus that. That was my final answer. All integrated. I don't care if I screwed up a sign somewhere. Huh? Yeah. So as you can see from the last half hour of class, you can go down rabbit holes with trigonometry because they loop. And you can get stuck. It's fine. You try something else. If, the teaching moment, if this was on a test and you tried that, first of all, I won't put that problem on the test. My problems will be shorter that I know you can finish them in an hour and a half. Huh? Yeah. No. So what I'm saying is if you start to go down a rabbit hole and you can't figure out where you're stuck at some points, like we were at that last one, we had all the integration done except for that one piece. And you're like, I can't figure out how to integrate this. Write it. If all your work is correct and that's the mistake you've made, you will get the vast majority of the points for that question. Okay? Because I'm looking for your thought process behind it. Okay? This is a teaching class. It's not life and death. So yes, I want the right answer. Yes, I want you to understand how to do it correctly. But it's also important that you understand where you're going with things. And if you get totally and utterly stuck, just say it. I'm stuck here. I can't go any further. It's fine. Because this, at least this way, I understand that you know what's going on. You've gotten to that point and you're at a bottleneck and you need to move on. That's fine. Okay? Totally acceptable. Not just because I screwed up this problem. That's normally how I do things. Because that's important for you to understand that thing and understand where you're getting stuck and be able to verbalize that in a way that doesn't frustrate you on your test. Because the worst thing that can happen is you go through, you do your test, and you get totally and utterly frustrated on like the second problem, and you're done. And you don't get any of the rest of the problems done. I don't want that to happen. Okay? Does that make sense? Okay. We're actually not done yet. We still have one more rule we have to look at. We still have to deal with tangents and secants. So tangents and secants have two rules. They're simpler, less chaotic than the sines and cosines with that, with both even. So you have, if secant is even, and if tangent is odd. Okay? So if secant is even, we do the first one. You're going to substitute u as tangent of x. And you're going to use the secant squared x equals 1 plus tangent squared x as the Pythagorean identity. What's the derivative of tangent of x? It's secant squared. So you're going to pull out a secant squared. That's why it needs to be even. Because when you pull it out, it still has to be even. And if you pull it even out of an even, you still get an even. So we pull out the secant squared x, and we're still left over with the even there. If tangent is odd, we're setting the u equals secant x. What's the derivative of secant x? It's secant x tangent x. So you pull out one of each. And now you're left with both even. Because you pulled one away from the tangent, which was odd. And the secant actually doesn't really matter in that respect. Okay? The bottom piece here, this part right here, is important because these are two rules that you just need to know. Okay, you're not gonna solve them out. You're not gonna find them. It's just like the other rules for sine and those like that. The integral of tangent of x is ln secant of x. The integral of secant of x is ln secant x plus tangent x. Those are just rules. Because sometimes you're going to be left with just a tangent or just a secant left. And we need to work with that. Sorry. Switch slides. You good with this slide so we can do two of them? Okay. All right. Tangent to the 6th x, secant to the 4th x. Which of those two rules am I using? First one says if secant's even in this problem. So that's what we're going to use. So that one said set u to be tangent of x. So u is tangent of x. So du is secant squared x dx. And it was 1 plus tangent squared x. So secant squared x equals 1 plus tangent squared x. All right, so my goal is to change everything that's left over into tangents. So we're going to pull out the secant squared x dx. So that is my du. And now that secant squared x has got to be changed into 1 plus tangent squared x. Okay. Have I lost anybody to that point right there? Now, this isn't a massively long problem that I shouldn't have chosen. All right. So now I've got my du, and everything else is in tangents. So now I can replace it with u's. So I have u to the 6th, 1 plus u squared du. So this can become u to the 6th plus u to the 8th. So I got u to the 7th over 7 plus u to the 9th over 9 plus c. So then we switch back. So I got tangent to the 7th x over 7 plus tangent to the 9th x over 9 plus c. And after the last problem, that one looks simple.
So you're finding the du.
So whenever we do u substitution is the du. So when you do u substitution, everything's got to be changed to u's because we're now integrating based on u and not x. So whenever you pick for u is, then you have to do the derivative of that to find d, which is the derivative of u. So that's in essence of u substitution. So that's actually not necessarily this used for this. U substitution is used for a lot of things. That was one of the things we briefly touched at the very beginning when we started looking at chapter 6. We did some very simple u substitution. So this is just using it to start doing the trig stuff. All right. What about this one? So this one, tangent's odd, right? So it said if tangent's odd, u is secant of x. So that means du is secant of x tangent x. And we still have our secant x equals 1 plus tangent squared x rule that I can still use. Okay, I don't have any secants in this problem. So what do we need to do? I need a secant somewhere. And I still need a secant tangent. So let's split this up. So if I take this as tangent squared x and tangent x, I can change this to secant squared x minus 1 tangent x. Which one?
Even.
But now I have addition and subtraction built into the problem. But yes, I might have to actually use that in the next step, but I have to do something before that point. All right. So what's next? Let's multiply this through and see what I got. So I got secant squared x, tangent x, minus, and I'm actually going to split this up, the tangent of x there. All right, so we've got secant squared x and tangent x, right? We now have a secant and a tangent on the same side of the problem, correct? So I can now use what I've already got up here with my u's. So I can change this to secant x tangent x dx. So this part right here is my du, and that's u. So I have the integral of u du, which is 1/2 u squared. So we have I have to delete a slide because I need another slide. That one too. So I've got one half secant squared x. And then what is the integral of tangent? So that's my final answer. All right. And we're done.